Something happened roughly 13 billion years ago that you are only seeing right now. Not a recording, not a simulation. The actual event, frozen in light, just now completing its journey to your eyes. That light has been traveling longer than the Earth has existed, longer than the sun has burned. And here's the part that will completely unravel your sense of reality. The object that sent that light is no longer where it appears to be. It is not even close. It has moved so far that if you try to travel to the place where it looks like it is, you would miss it by billions of light years. The universe has a trick it plays on every observer inside it. And once you understand that trick, you will never look at the night sky the same way again. If this kind of deep dive into the fabric of reality is something you enjoy, a quick like or subscribe really does help this channel keep going. It takes 2 seconds for you and it means everything to me. Now get comfortable, let's begin. There is a moment early in childhood when someone tells you that the stars are far away, and you nod and move on because the statement does not feel dangerous. Far away is the thing you understand. Your school is far away. The next town is far away. Far away means you will need some time to get there. But the distance that separates us from even the nearest star is not that kind of far. It is a different category of separation entirely. One that requires you to rebuild your understanding of distance from scratch. And the only honest way to do that is to start with the thing that connects us to those stars at all. Light. Light is the messenger. Every piece of information the universe has ever delivered to your eyes arrived as light. The face of someone you love, the surface of the moon, the orange smear of a sunset, the faint smudge of the Andromeda galaxy on a dark autumn night. All of it reached you the same way, as photons, tiny packets of electromagnetic energy traveling through space. And here is the thing that most people spend their entire lives not truly absorbing. Those photons do not arrive instantly. They travel. They take time. And the time they take, scaled up across cosmic distances, becomes one of the most profound and disorienting facts in all of science. The speed of light through a vacuum is 299,792.458 kilometers per second. In most contexts, we round that to 300,000 kilometers per second, and even that rounded figure is almost impossible to take in. In 1 single second, light covers 300,000 kilometers. To put that in some kind of perspective, the circumference of the Earth at the equator is roughly 40,000 kilometers. In 1 second, light could travel around the entire planet 7.5 times. Not 7.5 times in a minute, not 7.5 times in an hour. 7.5 times in 1 second, the time it takes to snap your fingers. This speed is not an accident, and it is not simply the speed that light happens to travel at. It is woven into the structure of the universe itself. It is the speed at which all massless particles must travel through empty space, and it is the ultimate speed limit of reality. Nothing with mass can ever reach it. Nothing can exceed it. Albert Einstein showed in 1905 that the speed of light in a vacuum is the same for every observer, regardless of how fast that observer is moving. Whether you are standing still or hurtling through space at half the speed of light, if you measure how fast a photon travels past you, you will always get the same answer: 299,000 792.458 kilometers per second. Always. Invariably. Without exception. This constancy has enormous consequences that we will return to throughout this story. But first, it is worth sitting with the fact that light has a speed at all. For most of human history, people assumed light was instantaneous. You opened your eyes and you saw things immediately. There was no detectable delay. So the intuitive conclusion was that light simply arrived the moment it was produced. The Greek philosopher Aristotle argued for instantaneous light. Even thinkers as brilliant as René Descartes maintained that light propagated without any delay. The idea that something so blindingly fast could still have a measurable, finite speed seemed almost absurd. And yet, it is true. And the story of how we found that out is one of the most elegant detective stories in the history of science. The first credible evidence came in 1676 from a Danish astronomer named Ole Rømer. He was stationed at the Paris Observatory, tasked with producing reliable tables of the movements of Jupiter's moons for use in navigation. The innermost large moon of Jupiter, a volcanic world called Io, orbits the planet very rapidly, completing a full orbit in just under 43 hours. Because of the geometry of its orbit and Jupiter's position, Io regularly passes behind the planet and then re-emerges on the other side. These eclipses happen on a predictable clockwork schedule, and Rømer was carefully recording them over months and years. What he noticed was subtle but undeniable. When Earth was on the side of its orbit that brought it closer to Jupiter, Io's eclipses seemed to occur slightly earlier than his tables predicted. When Earth had moved to the far side of its orbit, the eclipses ran late, sometimes by as much as 10 minutes. The discrepancy was not random noise. It correlated precisely and systematically with how far Earth was from Jupiter at the time of each observation. When Earth was moving toward Jupiter in its orbit, the eclipses ran ahead of schedule. When Earth was moving away from Jupiter, the eclipses fell behind. Rømer realized there was only one explanation. Light was taking time to travel. When Earth was closer to Jupiter, the light from Io's re-emergence had less distance to cover and arrived sooner. When Earth was farther away, the same light had more ground to cross and arrived later. The discrepancy he observed corresponded to the time it took light to cross the additional distance created by Earth's changing position in its orbit. He estimated that light took approximately 22 minutes to cross the full diameter of Earth's orbit around the Sun. His calculation was not perfectly precise because he did not know the exact size of Earth's orbit, but his estimate put the speed of light at roughly 200,000 kilometers per second, which is within the right order of magnitude. The precise value he calculated was off, but the discovery itself was revolutionary. Light was not instantaneous. Light had a speed. The scientific community of the time was divided. Some accepted Rømer's reasoning immediately, others were skeptical, but the evidence accumulated. In 1728, the English astronomer James Bradley discovered a phenomenon called stellar aberration. The slight apparent shift in a star's position caused by the motion of the Earth as it orbits the Sun. The direction you need to point your telescope to see a star shifts very slightly depending on which direction Earth is traveling at the time of observation, in the same way that rain falling straight down appears to angle toward you when you run through it. Bradley's measurements of stellar aberration provided an independent confirmation that light has a finite speed, and his calculation of that speed was considerably more accurate than rumors. By the late 19th century, physicists working in laboratories on Earth had refined the measurement dramatically. The French physicist Léon Foucault used a rotating mirror apparatus in 1850 to measure the speed of light with a precision that was remarkable for the technology of his era. Albert Michelson, the American physicist who would later become famous for a different kind of light experiment, spent decades refining these measurements using longer and longer baseline distances. By the 1880s, Michelson had pinned the speed of light down to within a few hundred kilometers per second of the accepted modern value. He continued refining the measurement until almost the end of his life, conducting his final experiment using a long evacuated tube through the mountains of California in the early 1930s. By the mid-20th century, with the development of atomic clocks and laser interferometry, the measurement had been refined to the point where the uncertainty was vanishingly small. In 1983, the international scientific community took the extraordinary step of removing the speed of light from the list of things that need to be measured at all. The meter was redefined. 1 meter is now officially the distance light travels in a vacuum in exactly 1,299,792,458th of a second. The speed of light is no longer a measured quantity with experimental uncertainty. It is exact by definition, a fixed cornerstone of the international system of units. The universe handed us its own speed limit, and we built our system of measurement around it. So light has a speed, 300,000 kilometers per second. And this means that light takes time to cross any distance. The larger the distance, the more time it takes. And in the context of the universe, which is incomprehensibly large, the time that light requires to cross the distances between objects becomes enormous. This is where the light year enters the story. And it is worth understanding what a light year actually is before we begin multiplying it by billions. A light year is simply the distance that light travels in 1 year. The word year in the name refers only to the duration used to calculate the distance. It is the answer to a single question. If light travels at 300,000 kilometers per second continuously for 1 full year, how far does it get? The answer requires multiplying the speed of light by the number of seconds in a year. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365 days in a year. Multiply those together and you get 31,536,000 seconds in a year. Multiply that by 300,000 kilometers per second, and the result is approximately 9,460,000,000,000 kilometers. 9,460,000,000,000 kilometers. This is 1 light year. Not a measure of time despite the word year appearing in it, a measure of distance. The distance light physically crosses in the span of 1 Earth year. To begin to appreciate what that distance means, it helps to build up to it gradually, starting with what light covers in smaller increments of time, because this is how the scale becomes real. Not by reciting a large number, but by watching the numbers accumulate step by step until the total becomes genuinely staggering. In 1 second, light travels 300,000 kilometers. As we established, these 7.5 laps around the circumference of the Earth. When you switch on a lamp, the photons from the bulb reach your eyes in a time so short it cannot be perceived by any biological system. A medium-sized room might be 5 meters across, and at 300,000 kilometers per second, light crosses 5 meters in about 17 billionths of a second. Your nervous system has no hope of detecting that delay. The light simply appears everywhere at once as far as your senses are concerned. But the light did travel. It took time. The time was just too short to notice. Scale up the distance even slightly, and the delay becomes real and measurable, and even consequential. The moon is roughly 384,000 kilometers from Earth on average. At the speed of light, crossing that distance takes approximately 1.3 seconds. 1.3 seconds sounds trivial until you think about what it meant for the Apollo astronauts who stood on the lunar surface and spoke to Mission Control in Houston. Every word they said took 1.3 seconds to reach Earth as a radio signal. Every response from Houston took another 1.3 seconds to reach them on the moon. There was a nearly 3-second gap embedded in every exchange, unavoidably, because even radio waves, which travel at the speed of light, need time to cross the distance between Earth and Moon. You can hear this delay clearly in the recordings. Both parties speak and then pause, and the pause is not politeness or hesitation. It is the physics of distance. Move to the sun, and the delay becomes impossible to ignore. The sun is approximately 150 million kilometers from Earth. Light from the sun's surface takes 8 minutes and 20 seconds to reach us. This is often mentioned as an interesting fact in a list of space curiosities, but consider what it actually means. The sun you are looking at right now is not the sun as it currently exists. It is the sun as it was 8 minutes and 20 seconds ago. If something catastrophic happened to the sun at this precise moment, if an enormous flare erupted or some unimaginable event began reshaping the star's surface, you would not know for 8 minutes and 20 seconds. For that entire interval, you will continue seeing a perfectly ordinary sun, while the real sun, the present tense sun, had already changed. There is no faster channel for that information. There is no way to check in on the sun's current status. The present state of the sun is, in a literal physical sense, inaccessible to you right now. This is not a philosophical technicality, it is a hard constraint imposed by the nature of reality. Information cannot travel faster than light. The present state of any distant object is, by definition, unavailable to you. All you can ever receive is information about what that object was doing at the moment its light departed. And the farther away the object, the further into the past you're looking. 1 light minute is approximately 18 million kilometers. 1 light hour is just over 1,080,000,000 kilometers. Saturn, at its closest to Earth, is about 1.1 light hours away. When the Cassini spacecraft was in orbit around Saturn from 2004 to 2017, every command sent from Earth took over an hour to arrive. Every photograph the spacecraft took had to be stored on board and then transmitted back at the speed of light, arriving more than an hour after capture. The scientists operating the mission could not respond in real time to anything the spacecraft observed. The communication delay was baked into every decision, every command sequence, every contingency plan. Saturn, one of the most beautiful objects in the night sky, visible to the naked eye and known to human observers since ancient times, is over 1 billion kilometers away, separated from any real-time response by more than an hour of light travel time. One light day is 24 light hours, corresponding to roughly 26 billion kilometers. The Voyager 1 spacecraft, launched in 1977 and currently the most distant human-made object from Earth, is approximately 22 to 23 light hours away from us as of recent measurements. It has been traveling for nearly 50 years, moving away from the Sun at roughly 17 kilometers per second, which is about 61,200 kilometers per hour, a speed so extreme by any human standard that it seems almost beyond comprehension. And yet, after nearly half a century of continuous travel at that speed through the vacuum of space with nothing to slow it down, Voyager has still not crossed even one full light day of distance from Earth. It is still, in cosmic terms, essentially next door. There is something quietly devastating about that fact. The fastest spacecraft humanity has ever sent into interstellar space, after 50 years of travel, has not yet crossed the distance that light covers in one day. We are not talking about reaching another star. We are not even talking about leaving the Sun's gravitational sphere of influence entirely. One light day, 24 hours at the speed of light, 50 years of rocket travel to cover not quite that much. The mismatch between the speeds we can achieve and the distances of the universe is not an engineering problem waiting for a better rocket. It is a feature of the cosmos at a scale that dwarfs anything our technology currently addresses. 1 light week, 7 light days, is about 181 billion kilometers. This scale, we are deep in the outer regions of the solar system, well beyond the orbit of Neptune, into the cold and thinly populated outer reaches where the Sun's light is so dim and distant that it appears as nothing more than an unusually bright star. Nothing built by human hands has ever been this far from Earth, and given current technology, nothing will reach this distance for generations. 1 light month is roughly 780 billion kilometers. At this distance, if you could somehow be positioned in space and look back at the inner solar system, the Sun would still be the brightest object in the sky by a considerable margin. But the familiar planets, the ones we see clearly from Earth with the naked eye, would be reduced to faint points, barely distinguishable from background stars without careful observation. Everything that humanity has explored directly, every planet any spacecraft has visited, every moon any probe has touched, all of it would be compressed into a tiny region around a single bright star in an otherwise ordinary sky. And 1 light year is 12 of those months. It is 52 light weeks. It is 365 light days. It is 8,760 light hours. It is 525,600 light minutes. It is 31,536,000 light seconds. Every one of those light seconds represents 300,000 kilometers of genuine physical distance. 31,536,000 of them, end to end, is 1 light year. 9,460 billion kilometers in total. Now we can begin to apply this unit to the actual universe and feel the weight of what it represents. The nearest star to our Sun, a red dwarf called Proxima Centauri, is 4.24 light years away. This makes it, in astronomical terms, practically a neighbor. In human terms, it is an almost incomprehensible separation. The light entering your eye when you look at Proxima Centauri tonight left that star 4.24 years ago. You are not seeing Proxima Centauri as it currently exists. You are seeing it as it was 4 years ago. If some dramatic change occurred at that star last Tuesday, you will not find out for more than 4 years. There is nothing you can do to learn about it sooner. No instrument, no technology, no theoretical advance changes this. The universe has simply arranged itself so that the present state of any object more than a certain distance away is, at this moment, completely inaccessible. To travel to Proxima Centauri with any propulsion technology we currently possess, or could plausibly build in the near future, the journey would take thousands of years. The Parker Solar Probe, the fastest spacecraft ever built by humans, reaches speeds of approximately 192 kilometers per second at its closest approach to the Sun. At that speed, the journey to Proxima Centauri would require approximately 6,600 years. Not decades, not centuries, over 6 millennia. You could have launched your spacecraft before writing had even been invented, before the first cities existed, at a time when human beings were still transitioning out of the Stone Age, and it would still be thousands of years from arriving today. 1 light year, just one of the 4.24 that separate us from the nearest star, is a distance so vast that the fastest thing humans have ever built would need over 1,500 years to cross it. Sirius, the brightest star in the night sky, blazing from the constellation Canis Major with a blue-white intensity that makes it unmistakable on a clear night, is 8.6 light years away. The light arriving at Uranus from Sirius tonight left that star 8.6 years ago. Vega, another of the brightest and most recognizable stars in the northern sky, sits 25 light years away. The light you see from Vega departed that star a quarter century ago. If you are 25 years old tonight, the light from Vega currently hitting your eyes began its journey the year you were born. When that photon was released into space, you had not yet taken your first breath. Betelgeuse, the famous red supergiant marking the shoulder of Orion, is approximately 700 light years away. The light you receive from Betelgeuse tonight began its journey around the year 1325, the early 14th century, at a time when the Black Death had not yet reached Europe, when the 100 Years' War between England and France had not yet begun, when the poet Dante had only recently died, and the city of Tenochtitlan was being founded by the Aztecs. That 700-year-old light had been crossing the void continuously since then, traveling at 300,000 kilometers per second through the darkness between stars, and tonight it arrives at your eye. But here is the detail about Betelgeuse that makes all of this genuinely unsettling, rather than merely interesting. Betelgeuse is a massive star in the late stages of its life. Astrophysicists are confident that it will explode as a supernova at some point in the relatively near astronomical future, which could mean anywhere from a few thousand to 100,000 years from now. When it does, it will briefly shine as brightly as the full moon, visible even in daylight. But here's the thing. It may have already exploded. There is no way for us to know. If Betelgeuse detonated in a supernova 600 years ago, that explosion happened too recently for its light to have reached us yet. We would still be receiving pre-explosion light and watching a star that no longer exists as a star. The explosion's light would still be centuries away, traveling toward us at 300,000 kilometers per second, and we would have no warning of its arrival until it appeared in the sky. We are watching a potentially dead star and calling it alive simply because the news has not arrived yet. The light year, then, is not just a unit of distance, it is a unit of temporal separation. Every light year of distance between you and an object is a year of past you are observing rather than present. The sky, when you truly understand this, is not a display of where things are. It is a layered archive of where things were. The nearby stars show you a relatively recent past, a few years to a few centuries ago. The bright stars of our galaxy show you a past stretching from decades to thousands of years. Distant galaxies show you millions and tens of millions of years into the past. And the most ancient light of all, which we will get to in detail later, shows you the universe as it was nearly 14 billion years ago. Every direction you look is a different depth of time. The night sky is a time machine, and you are always looking backward. Now, with the light year established as a unit and its physical and temporal meaning understood, we can turn our attention to the distances that light crosses not just between individual stars, but across the full span of cosmic time. Because the scale of the nearby universe, 4 light years to Proxima Centauri, 8.6 to Sirius, 700 to Betelgeuse, is still just the entrance hall. The true structure of the cosmos operates at distances where those stellar separations become so small they are invisible, where millions and billions of light years are the relevant units, and where the behavior of space itself during the journey of a photon changes the nature of the question we are asking. Light does not simply travel through an inert, static backdrop. It travels through a universe that is actively changing. And what that means for how far light actually travels, and for the relationship between the distance light has covered and the present-day location of its source, is one of the deepest and most surprising stories in the whole of modern science. Take everything we have established about the light year and now apply it to the actual architecture of the cosmos. Because the distances between individual stars, while staggering by human standards, are merely the smallest rung on a ladder that climbs through scales so extreme that the word vast becomes almost comically inadequate. When we talk about how far light actually travels across millions and billions of years, we are not extending the star-to-star logic by a modest amount. We are multiplying it by factors that turn the already incomprehensible into something that language genuinely struggles to carry. And the only way to make it real is to walk through it systematically, pausing at each level of scale long enough to feel the weight of what is actually being described. Let us begin with our own galaxy, because even within the Milky Way, the distances involved are so large that they permanently reframe the idea of a neighborhood. The Milky Way is a barred spiral galaxy stretching approximately 100,000 light years from one edge of its disk to the other. 100,000 light years. Light, traveling at 300,000 kilometers per second, without pause, without slowing, without any interruption whatsoever, would require 100,000 years to cross our own galaxy from one side to the other. To put that duration in perspective, the entire span of recorded human history, from the earliest writing systems in Mesopotamia to the present day, represents roughly 5,000 to 6,000 years. That is between 5 and 6% of the time it would take light to make a one-way trip across our galaxy. The full history of human civilization, every empire, every invention, every war, every work of art and science and philosophy ever produced, would occupy less than 1/16th of that journey. Our sun sits roughly 26,000 light years from the galactic center, embedded in a minor spiral arm called the Orion Spur, positioned about halfway between the center and the outer edge of the disk. When astronomers observed the densely packed region of stars surrounding the supermassive black hole at the heart of our galaxy, the object known as Sagittarius A star, they are observing it as it was 26,000 years ago. At that moment in Earth's history, the last ice age was still ongoing. Humans were creating cave paintings on the walls of European caves, hunting woolly mammoths with stone-tipped spears, and living in small nomadic groups with no agriculture, no permanent settlements, no written language of any kind. The galactic center as it exists tonight, in real time, is simply not available to us. We are watching a 26,000-year-old recording projected across the sky, and we will continue watching that same era of galactic history until a newer transmission arrives. The densest and most spectacular regions of the Milky Way, the central bulge and the core, are shrouded in dust and gas that blocks visible light almost entirely. Astronomers must use radio waves, infrared radiation, and X-rays to see through this obscuring material and study what lies within. The light they detect in those wavelengths still carries the same time delay. The infrared light from stars orbiting Sagittarius A star, which has been used to map those orbital paths with extraordinary precision and confirm the presence of the supermassive black hole, is still 26,000-year-old information. The exquisite precision of the measurements does not change the age of the light. The Milky Way contains somewhere between 100 billion and 400 billion stars. The most probable estimate sits closer to 200 to 300 billion. Every one of those stars is separated from its nearest neighbors by distances typically measured in light years. The average distance between stars in the disk of the Milky Way is roughly a few light years, though this varies considerably depending on location. Near the dense central bulge, stars are packed much more tightly. In the outer regions of the disk, they are more widely spaced. But even in the most densely populated regions of our galaxy, stars are separated by distances that light takes years to cross. The Milky Way is not a solid object or a dense cloud. It is overwhelmingly empty space, with stars scattered through it at enormous separations, connected to each other and to us only by the light they radiate across those voids. Now, step outside the galaxy entirely. The first major boundary we cross when leaving the Milky Way takes us into the local group, the collection of roughly 50 to 60 galaxies that are gravitationally bound to each other and share a common motion through space. The dominant members of the local group are the Milky Way and the Andromeda Galaxy, also designated Messier 31, which at 2,500,000 light-years away is the most distant object visible to the naked eye under ideal conditions. That faint, elongated smudge in the constellation Andromeda that you can just barely detect on a dark, clear night is a galaxy containing roughly 1 trillion stars. And the light reaching your eyes from it left those stars 2,500,000 years ago. 2.5 million years. At that moment, our ancestors on Earth were early members of the genus Homo, likely Homo habilis or a closely related species, making simple stone tools in Africa with brains significantly smaller than modern humans and no language as we would recognize it today. The entire subsequent history of human evolution, the development of Homo erectus, the emergence of archaic Homo sapiens, the appearance of modern Homo sapiens roughly 300,000 years ago, the development of complex language, the invention of fire-making, the colonization of every continent, the emergence of art and music and religion, the development of agriculture and cities and writing, all of recorded civilization, all of it has unfolded during the time that the light currently reaching your eye from Andromeda was crossing the space between our galaxies. Every photon of Andromeda's light in your field of view tonight departed before the human lineage had produced anything we would recognize as human. The Andromeda galaxy is approaching us. The gravitational attraction between the Milky Way and Andromeda, combined with the motions of both galaxies through the local group, means the distance between them is slowly closing. In approximately 4.5 billion years, the two galaxies will begin a process of merging. But the light you see from Andromeda tonight is not the Andromeda that is closing in on us right now. It is the Andromeda of 2.5 million years past, frozen in the light that left it at that distant moment, and has been traveling toward us ever since. Beyond the local group, the next major structure is the Virgo cluster, a massive concentration of between 1,000 and 2,000 galaxies located approximately 54 million light-years from Earth. The Virgo cluster is the dominant gravitational center of the larger Virgo supercluster, of which the local group is a peripheral member. The light arriving from the Virgo cluster left those galaxies 54 million years ago. On Earth at that time, the extinction of the non-avian dinosaurs had occurred roughly 12 million years earlier, and early mammals were diversifying rapidly across a warming planet. The first primates had appeared, small tree-dwelling creatures with grasping hands and forward-facing eyes, but nothing remotely resembling a human being existed, or was anywhere close to existing. The line that would eventually produce human beings was still tens of millions of years of evolution away from anything we would recognize. And while all of that evolution was unfolding on one small planet, the light from the Virgo cluster was crossing the 54 million light-years of space between there and here. The largest member of the Virgo cluster, the giant elliptical galaxy Messier 87, contains approximately 1 trillion stars and hosts one of the most massive black holes ever directly imaged. Its central black hole, which was photographed in 2019 by the Event Horizon Telescope collaboration in a landmark achievement of observational astronomy, has a mass approximately 6.5 billion times that of our Sun. The image of that black hole that was released to the world was assembled from light that had been traveling for 54 million years before being captured by radio telescopes on Earth. The shadow of a black hole, 6.5 billion solar masses worth of collapsed matter, recorded from a distance of 54 million light years. The photons that formed that image were released before humans existed, before apes existed, before the lineage that would produce primates had diverged into anything we would today classify as a primate. Moving outward in distance and therefore backward in time, we reach galaxy clusters and superclusters at hundreds of millions of light years. The Perseus cluster, one of the most massive galaxy clusters in the observable universe, and an extraordinarily bright source of X-ray radiation, sits approximately 240 million light years from Earth. Its light has been traveling for 240 million years. When it began its journey, the Triassic period was already well underway on our planet. The Permian-Triassic extinction event, the largest mass extinction in Earth's history, which eliminated roughly 96% of all marine species and 70% of terrestrial vertebrate species, had occurred roughly 12 million years before. The first dinosaurs had not yet appeared. Pangaea, the supercontinent, was still largely intact. The world was dominated by reptiles and early mammal-like creatures called therapsids that would eventually give rise to the mammalian line. That was the Earth when the light from the Perseus cluster departed on its 240 million light-year journey to our telescopes. The Coma cluster, another enormous concentration of galaxies that has been extensively studied as one of the first pieces of evidence for dark matter, is approximately 320 million light years away. Its light has been traveling since before any dinosaur walked the Earth. The age of the dinosaurs, that entire 165 million year dynasty, began and ended during the time that light from the Coma cluster was crossing the universe toward us. Every species of dinosaur that ever lived, from the earliest small theropods of the Triassic, through the giants of the Jurassic, to the iconic forms of the Cretaceous, appeared, flourished, and vanished while those photons were in transit. Now we enter the domain of billions of light years, where the distances become so enormous that the changes in the universe during the light's journey are no longer just biological and geological, but cosmological. At 1 billion light years, we are observing galaxies as they were 1 billion years ago, when the universe was approximately 12.8 billion years old. The Sun and Earth had already formed by then, having condensed from their natal cloud of gas and dust roughly 4.5 billion years ago. Life had already existed on Earth for over 3 billion years by the time that light departed. The universe at 1 billion light years of distance looks broadly similar to the universe today, but with subtle differences in the distribution and properties of galaxies that cosmologists can measure precisely. At 3 billion light years, we see the universe as it was 3 billion years ago, when the Sun and Earth did not yet exist. The matter that would eventually form our solar system was still dispersed as gas and dust, within an earlier generation of stars or floating between them in the interstellar medium. There was no Sun, there was no Earth, there was no solar system. The atoms that compose your body had not yet been assembled into any planet. They were the raw materials of a future that had not happened yet. And the light from galaxies at that distance, the light currently captured by our telescopes, left those galaxies before any of that future was realized. At 5 billion light years, the universe was significantly younger and more active than it is today. Star formation rates across the cosmos were higher. Galaxies were more frequently colliding and merging. The universe had not yet reached the settled, relatively mature state it inhabits today. The Hubble Space Telescope's deep field images, taken by pointing the telescope at what appeared to be nearly empty patches of sky and allowing it to collect light for days or weeks at a time, revealed thousands of galaxies at these kinds of distances, each one a snapshot of a different era of cosmic history, frozen in the light that left it at the moment of its emission and arriving at our detectors billions of years later. At 7 billion light years, something interesting happens in the history of the universe. This is roughly the era at which the expansion of the universe transitioned from decelerating to accelerating. For the first roughly 7 billion years after the Big Bang, the expansion was slowing down under the gravitational pull of all the matter in the universe. Gravity was dominant, pulling everything toward everything else, gradually putting a brake on the outward rush of the Big Bang. But at around 7 billion years after the Big Bang, dark energy, the mysterious component of the universe whose nature remains one of the great unsolved problems in physics, began to dominate over the gravitational deceleration. From that point onward, the expansion of the universe began to speed up. Galaxies, distances corresponding to that era of transition, are showing us the universe at the hinge point of cosmic history. The moment when the fate of the universe changed from potentially recollapsing into a big crunch to expanding forever with accelerating speed. That transition is embedded in the light that has been traveling toward us for 7 billion years. At 10 billion light years, we are looking at a universe that was only 3.8 billion years old. The Milky Way existed in a recognizable form at this point, but it was younger and more active. Many of the stars that currently populate our galaxy had not yet formed. The Sun would not form for another 5.5 billion years. The light from galaxies at 10 billion light years left those galaxies when our galaxy was in a relatively early and vigorous phase of its life, churning through gas and forming new stars at a higher rate than it does today. The Hubble Space Telescope and subsequently the James Webb Space Telescope have pushed observations to distances that correspond to light travel times of over 13 billion years, reaching back to when the universe was only a few hundred million years old. At these distances, we are looking at the first generation of galaxies, the earliest structures to condense out of the primordial gas following the Big Bang. These objects look nothing like the galaxies we see in the nearby universe. They are smaller, clumpier, more irregular in shape, intensely blue from the massive burst of star formation occurring within them as enormous quantities of pristine hydrogen gas collapse into stars for the first time. They are the universe's rough draft, the first attempts at building large-scale structure from the raw material of the Big Bang. The James Webb Space Telescope, with its extraordinary infrared sensitivity and its position far from Earth in a stable orbit 1.5 million kilometers away, has detected individual galaxies at redshifts, corresponding to a time when the universe was less than 300 million years old, barely 2% of its current age. The light from these objects has been traveling for over 13.5 billion years. Every second of that journey, those photons covered 300,000 kilometers. Over 13.5 billion years. The total distance they physically traversed, moving at their constant speed through expanding space, amounts to over 13.5 billion light years of actual travel distance. That is the raw, physical answer to how far light travels over that span of time. It moves at 300,000 kilometers per second, and in 13.5 billion years of doing so, it accumulates 13.5 billion light years of distance covered. Let that figure sit in your mind for a moment. 9,460,000,000,000 kilometers in 1 light year. Multiply that by 13 billion, and you have the distance a photon covers in 13 billion years of travel. It is a number so large that it defeats every analogy drawn from ordinary experience. If you try to write it out in kilometers, the number would have 22 digits. No human activity, no engineering project, no measurement we make in daily life comes within many orders of magnitude of this scale. The observable universe is not large in the way that a country or a continent or even a planet is large. It is large in a way that is categorically different from any human scale of size. And the light year and the distances it accumulates over billions of years are the units that make that difference legible. But here is where the story deepens in a way that the simple multiplication of speed and time cannot capture on its own. The distances just described, 13 billion light years for the most ancient photons, 54 million light years for the Virgo cluster, 2.5 million light years for Andromeda, are the light travel distances. They are the distances physically covered by the light during its journey. They correspond directly to the time elapsed. 1 billion years of travel time means 1 billion light years of distance covered. The math is clean and the logic is straightforward. But these light travel distances are not the same as the present-day distances to the objects that emitted the light. The source galaxy is no longer where it was when the light departed. The universe has been expanding the entire time those photons were in transit, and that expansion has carried the source galaxy and the Milky Way farther apart than they were at the moment of emission. The light covered 13 billion light years of physical distance over its 13 billion year journey, but the object that emitted it is now, in terms of present-day separation, approximately 46 billion light years away. This discrepancy, and it is a large one, requires understanding what is actually happening to space during the light's journey. And to understand that, we need to understand what cosmic expansion actually means at the level of the photon. When a photon is emitted by a distant galaxy and begins moving toward the Milky Way, it moves through its local region of space at the speed of light. This is always true. In any small patch of space, locally, light always moves at 300,000 kilometers per second. But the space that photon is moving through is not static. The universe is expanding, which means new space is continuously being generated between all points that are not gravitationally bound together. The photon is making genuine progress toward us, but the space between its origin and its destination is simultaneously growing. The total distance the photon must cover is not fixed. It increases as the journey proceeds, because the universe is creating new distance even as the photon is eliminating old distance. Think of it this way. Imagine you are trying to swim across a river, but the river is getting wider as you swim. You are making genuine forward progress at your maximum swimming speed, but the far bank is receding because the river itself is expanding. Whether you ever reach the far bank depends on how fast the river is expanding relative to how fast you can swim. If the expansion is slow enough, you will eventually make it. If the expansion is too fast, you will never reach the other side, regardless of how hard you swim. Photons traveling toward us from the early universe are in exactly this situation, swimming across an expanding river, and whether they ever make it depends on the expansion rate of the universe at every point along their journey. In the early universe, the expansion was rapid but decelerating. Over time, as matter diluted and dark energy began to dominate, the expansion first slowed in its deceleration and then began accelerating. Photons that were emitted when the universe was very young, even those emitted from regions that were already receding from us faster than light, due to the rapid early expansion, were nevertheless able to eventually make it to us because the expansion initially decelerated enough to allow them to close the gap over time. They have been swimming across the widening river for over 13 billion years, and tonight they arrive. The result of this dynamic, this interplay between photon motion and cosmic expansion, is that the present-day location of the source is dramatically farther away than the light travel distance would suggest. A galaxy whose light has traveled 13 billion years to reach us is now approximately 46 billion light years away. The universe's expansion has added roughly 33 billion light years of additional separation between us and that galaxy beyond the distance the light actually covered. This is not an error or a paradox. It is the correct, well-tested result of applying the equations of general relativity to an expanding universe. The light travel distance and the present-day distance are two different and equally valid ways of describing the separation between us and a distant object. And they give different answers because the universe has been growing during the entire time the light was in transit. This also means that the observable universe, the sphere of space from which we can receive signals, is larger than you might expect from simply multiplying the speed of light by the age of the universe. If the universe was static, not expanding, then the observable universe would be at most 13.8 billion light years in radius, corresponding to the distance light can travel in the age of the universe. But because of expansion, the present-day distances to the most distant observable objects are approximately 46 billion light years. The observable universe has a radius of about 46.5 billion light years, giving it a total diameter of approximately 93 billion light years. This is the correct, physically meaningful size of the observable universe. Not 27.6 billion light years across, but 93 billion light years across, nearly 3.5 times larger than the naive estimate from light travel time alone. Within this sphere of 93 billion light years in diameter, astronomers estimate there are approximately 2 trillion galaxies. The number has been revised upward from earlier estimates, as deeper surveys have revealed more galaxies in faint, distant populations that previous telescopes could not detect. 2 trillion galaxies, each containing anywhere from millions to hundreds of billions of stars. The total number of stars in the observable universe is estimated at around 200 billion trillion, which is a 2 followed by 23 zeros. Most of these stars are separated from their nearest neighbors by distances measured in light years, and most of those stellar systems are separated from us by distances measured in millions or billions of light years. Every one of those galaxies visible in our deepest telescope images is a collection of ancient light, photons that departed those stellar populations millions or billions of years ago, and have been crossing the expanding universe ever since. The image captured by a telescope is not a snapshot of where those galaxies are. It is a snapshot of where they were, assembled from light that is older than anything on Earth in many cases, arriving at our detectors as the final act of a journey that began before our sun existed, when the James Webb Space Telescope released its first deep field image in 2022, showing thousands of galaxies in extraordinary detail across a patch of sky smaller than a grain of sand held at arm's length. Every galaxy in that image was a messenger from the past. Some were relatively nearby, their light only millions of years old. Others were at redshifts corresponding to light travel times of over 13 billion years. In a single image, the telescope captured cosmic history spanning over 13 billion years of time, all compressed into photons arriving simultaneously at its detectors, each having traveled a different distance, each carrying information about the universe at a different point in its evolution. The image was not a view of the universe as it is. It was a cross-section through cosmic time, deeper layers being older, closer layers being younger, assembled into a single frame by the physics of light travel and expansion. The physical reality underlying all of these observations is consistent and clear. Light travels at 300,000 kilometers per second. In 1 year, it covers 9,460,000,000,000 kilometers. In 1 million years, it covers 9,460,000,000,000 times 1 million kilometers. In 1 billion years, it covers 9,460,000,000,000 times 1 billion kilometers. These are the actual physical distances that light traverses in those timeframes. The distances covered by the photons themselves during their journeys through space. Every second of every journey, 300,000 kilometers. No variation, no slowdown, no pause. For millions and billions of years, across the void between galaxies and superclusters, and across the full diameter of the observable universe, 300,000 kilometers per second. The universe is old enough and large enough that light emitted at its earliest transparent moments has had time to travel over 13 billion light years, and is only now, in this cosmic era, arriving at detectors built by a species that did not exist for the overwhelming majority of that photon's journey. The light has been traveling since before the Earth formed, since before the sun ignited, since before any rocky planet existed anywhere in the Milky Way. It has been crossing the universe for all of that time, carrying within it the imprint of its source, the signature of its emission, the fingerprints of the physics of the early cosmos, and arriving here now at our telescopes to be collected and decoded and turned into knowledge about the universe's infancy. That is what light actually does over billions of years. It travels continuously, without pause, at 300,000 kilometers per second, across distances that accumulate into billions of light years of physical journey, carrying information across the full span of cosmic time from sources that are no longer where they appear to be, from eras that no longer exist, from a universe that has grown and changed beyond recognition during the crossing. And the extraordinary thing is that we can read it. We can point instruments at the sky, collect those ancient photons, analyze the patterns they carry, and reconstruct from them the history of a universe that has been evolving for nearly 14 billion years. The light has been traveling all that time, and we've arrived just in time to catch it. The most important and most consistently misunderstood fact in observational cosmology is this. When you look at a distant galaxy, the distance you measure from its light travel time is not the distance to that galaxy. Not approximately. Not within a margin of error. The two numbers, the light travel distance and the present day distance, can differ by factors of 2 or 3 or more, depending on how ancient the light is. And the reason for this discrepancy is not a technicality or a measurement limitation. It is a physical reality about the nature of space itself. Space is not a fixed stage on which the universe performs. It is the dynamic medium that has been growing continuously since the first moments after the Big Bang, stretching the distances between everything inside it, carrying galaxies apart from each other, not because those galaxies are moving through space, but because the space between them is becoming more space. Understanding this distinction changes everything about how we interpret cosmic distances and what it means for light to travel across billions of years. The discovery that the universe is expanding came not from theory, but from observation, and it arrived in stages that each required revising a deeply held assumption about the nature of the cosmos. The critical thread begins with a question that seems simple on the surface. What are the fuzzy, nebulous patches of light scattered across the sky that do not resolve into individual stars even through the most powerful telescopes available in the early 20th century? Are they clouds of gas within the Milky Way? Or are they something else entirely? Something vastly farther away? The answer came from a technique involving a particular class of variable stars called Cepheid variables. These are stars that pulsate in brightness with a very regular period, brightening and dimming in a cycle that repeats over days or weeks. The key property of Cepheid variables, discovered by the astronomer Henrietta Swan Leavitt, working at the Harvard College Observatory in 1912, is that there is a precise mathematical relationship between the period of a Cepheid's pulsation and its intrinsic luminosity, meaning how much light it actually produces. A Cepheid with a longer pulsation period is genuinely more luminous than one with a shorter period. This relationship holds with remarkable consistency across all Cepheid variables. This matters enormously for distance measurement because it transforms a Cepheid into what astronomers call a standard candle. If you observe a Cepheid variable and measure how long its cycle takes, you know from Leavitt's relationship how intrinsically bright it is. You can then compare its intrinsic brightness to how bright it appears in the sky. Stars that are farther away appear dimmer, following a precise mathematical law called the inverse square law, which states that apparent brightness decreases with the square of the distance. A star twice as far away appears 4 times dimmer. A star 10 times as far away appears 100 times dimmer. By comparing the intrinsic brightness you derived from the period to the observed apparent brightness, you can calculate exactly how far away the Cepheid must be. The technique works across enormous distances as long as the Cepheid is bright enough to be detected and its period can be measured. Edwin Hubble, working at the Mount Wilson Observatory in California in the 1920s, with what was at the time the world's largest telescope, a 2.5-meter reflector, used Cepheid variables to settle the debate about the fuzzy nebulae once and for all. He identified individual Cepheid variables within the Andromeda Nebula, measured their pulsation periods, calculated their intrinsic brightnesses from Leavitt's relationship, and derived the distance. The result was unambiguous and revolutionary. Andromeda was not a gas cloud within the Milky Way. It was a separate galaxy of stars, located at a distance so vast that it was clearly far outside our own galaxy's boundaries. The universe was not the Milky Way. The Milky Way was one island in an ocean of islands, and the ocean was enormous. But Hubble did not stop at determining distances. He also measured what is called the redshift of the light coming from these distant galaxies. And what he found when he combined the distances with the redshifts transformed our understanding of the universe at the deepest level. Redshift occurs when the wavelength of light is stretched. Visible light is characterized by its wavelength, which corresponds to its color. Short wavelengths appear blue or violet. Long wavelengths appear red. When a source of light is moving away from an observer, the light waves are stretched out, shifted toward longer wavelengths, shifted toward the red end of the spectrum. This is the cosmological equivalent of the Doppler effect, the same phenomenon that makes a passing ambulance's siren drop in pitch as it recedes. For sound, motion away from you stretches the sound waves, lowering the pitch. For light, motion away from you stretches the light waves, reddening the color. Hubble found that virtually every galaxy he studied beyond the local group showed this redshift. Their light was systematically shifted toward longer wavelengths, compared to what the same atomic transitions produce in a laboratory on Earth. This meant they were receding from us, and the more distant a galaxy was, the greater its redshift, the faster it appeared to be moving away. The relationship was nearly linear. A galaxy twice as far away had twice the redshift. A galaxy 10 times as far away had 10 times the redshift. This pattern, now called Hubble's law, encoded something profound. The universe was expanding. Not in the sense that galaxies were flying away from each other through pre-existing static space, but in the deeper and more startling sense that space itself was growing, that the fabric of the cosmos was stretching, and that galaxies were being carried apart by that stretching, the way raisins embedded in rising bread dough are carried apart as the dough expands. Hubble's constant, the number that quantifies the current rate of this expansion, describes how fast galaxies are receding from each other per unit of distance. Modern measurements, using a combination of Cepheid variables, type 1a supernovae, and the detailed structure of the cosmic microwave background, place the value of Hubble's constant at approximately 67 to 73 kilometers per second per megaparsec. A megaparsec is about 3.26 million light years. What this means practically is that for every 3.26 million light years of distance between 2 points in the universe, those points are being carried apart at roughly 67 to 73 kilometers per second by the expansion of space. Double the distance, and the recession rate doubles. Triple the distance, and the recession rate triples. The recession velocity is directly proportional to the distance. There is currently a tension in cosmology around the precise value of Hubble's constant that is worth mentioning, because it represents one of the most important unresolved puzzles in modern physics. When the constant is measured using the cosmic microwave background and the physics of the early universe, The result is approximately 67.4 kilometers per second per megaparsec. When it is measured using Cepheid variables and Type 1a supernovae in the local universe, the result is consistently closer to 73 kilometers per second per megaparsec. This discrepancy of roughly 9% sounds small, but it is far larger than the measurement uncertainties of either method, and it has persisted and actually sharpened as both measurement approaches have become more precise. Either one of the measurements is affected by an unidentified systematic error, or there is genuinely new physics operating in the universe that current models do not account for. The mystery remains open, and resolving it is one of the central challenges facing observational cosmology today. Now, the expansion of space means that when a photon is emitted by a distant galaxy and begins traveling toward the Milky Way, it is not crossing a fixed distance. The distance it must cover is changing as it travels, because the space between its origin and its destination is growing the entire time. Every second that the photon is in transit, more space is being generated between the source and the Milky Way. The photon never stops moving at the speed of light through whatever space it occupies locally. But the total gap it needs to close is not static. It is a moving target, growing continuously due to the expansion. Whether a photon emitted by a distant galaxy can ever reach us depends on the balance between the photon's speed through local space and the rate at which expansion is adding new distance between the source and the destination. In the early universe, the expansion rate was high, but decelerating rapidly. Matter was densely packed, and gravity was slowing the expansion down. During this phase, photons emitted from regions that were at the time receding faster than light could still eventually reach us, because the expansion was slowing, and as it slowed, the photons were able to close the gap. Think of it as running toward a destination on a treadmill that is gradually slowing down. The treadmill is moving against you, but it is decelerating, so eventually you gain ground and make it to the end. This is the mechanism by which the observable universe is larger than the naive light travel calculation would suggest. Photons that began their journeys from regions that were already more than 13.8 billion light years away have been able to reach us because the expansion rate has changed during their journey. The deceleration of the expansion in the early universe, followed by the eventual shift to accelerating expansion driven by dark energy, created the particular expansion history that results in the observable universe having a radius of 46.5 billion light years rather than 13.8 billion. The redshift of a distant galaxy is not simply a measure of how fast that galaxy is moving through space. For galaxies at large distances, the recession is not motion through space at all. It is the growth of space between us and them. The light from a distant galaxy is redshifted because the space it has been traveling through has expanded during its journey, stretching the wavelengths of the light in proportion to the total expansion that has occurred since the light was emitted. A galaxy with a redshift of 1 means the universe has expanded by a factor of 2 since the light was emitted. A galaxy with a redshift of 2 means the universe was 3 times smaller when that light departed. The galaxy with the highest confirmed redshifts detected by the James Webb Space Telescope have values above 10, meaning the universe was more than 11 times smaller in all linear dimensions when those photons began their journey. This relationship between redshift and cosmic expansion allows astronomers to use redshift measurements as a proxy for distance, time, and the state of the universe at the moment of emission. By measuring the redshift of a galaxy's light, which requires spectroscopy, spreading the light into its component wavelengths, and identifying the characteristic patterns of atomic emission and absorption at shifted positions, astronomers can determine exactly how much the universe has expanded since that light was emitted. From this, using the known expansion history of the universe derived from multiple independent lines of evidence, they can calculate both the light travel time and the present-day co-moving distance, which is the distance to the galaxy as it exists in the universe right now. Type 1. As supernovae played a pivotal role in revealing one of the most shocking discoveries in the history of cosmology. A Type 1. A supernova occurs when a white dwarf star in a binary system accumulates enough mass from its companion to exceed a critical threshold called the Chandrasekhar limit, approximately 1.4 solar masses, at which point a runaway nuclear fusion reaction ignites throughout the white dwarf and detonates it catastrophically. Because this explosion is triggered by reaching the same mass threshold every time, Type 1a's supernovae have very nearly the same intrinsic peak luminosity regardless of where in the universe they occur. Small corrections can be applied based on how quickly the supernova brightens and fades. After these corrections, Type 1a supernova become extraordinarily precise, standard candles, bright enough to be observed at distances of billions of light years. In the late 1990s, two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, used Type 1a supernova at large distances to measure the expansion history of the universe. The expectation, based on the known matter content of the universe, was that the expansion should be decelerating. Gravity should be slowing things down. The distant supernovae should appear slightly brighter than a universe expanding at a constant rate would predict, because gravity should have been pulling things back, meaning the expansion was faster in the past and slower now, meaning less distance covered than constant expansion would give, meaning objects at a given redshift are slightly closer than naive estimates suggest, and therefore slightly brighter. What the teams found was the opposite. The distant supernovae were dimmer than expected. They were farther away than they should be if the expansion were decelerating. The expansion was not slowing down, it was speeding up. The universe was accelerating in its expansion. This discovery, announced in 1998 and recognized with the Nobel Prize in Physics in 2011, was the first direct evidence for dark energy, the mysterious component of the universe that is driving this acceleration. Dark energy does not behave like matter. Matter dilutes as the universe expands. Pour the same amount of matter into a larger volume, and its density decreases. Gravity weakens. Dark energy, by contrast, has a nearly constant energy density regardless of the volume of space. As the universe expands, the amount of dark energy per unit volume stays approximately the same, which means the total amount of dark energy grows as space grows. This behavior is consistent with dark energy being a property of space itself, an energy inherent to the vacuum, present everywhere and always at the same density. Einstein had actually incorporated a similar concept into his equations of general relativity in 1917, calling it the cosmological constant, a term he later described as his greatest blunder when it seemed the universe was static and the term appeared unnecessary. The discovery of accelerating expansion rehabilitated the cosmological constant entirely. The consequence of dark energy's constant density is that as the universe expands and matter thins out, dark energy becomes proportionally more dominant. Matter's contribution to the universe's total energy budget decreases over time as it dilutes, while dark energy's contribution remains constant or grows. Roughly 7 billion years after the Big Bang, dark energy crossed the threshold of becoming the dominant component of the universe's energy content, and from that point forward, the expansion stopped decelerating and began accelerating. The universe today is approximately 68% dark energy, 27% dark matter, and only 5% ordinary matter. The atoms, molecules, stars, planets, and everything built from them that we can directly observe and interact with. The acceleration of expansion driven by dark energy has a profound consequence for what any observer can ever know about the universe. The consequence of this acceleration is that there exists a boundary, a cosmic event horizon, beyond which any light emitted today can never reach us, and whose full implications we are about to explore. There is an important distinction between the cosmic event horizon and the edge of the observable universe. The observable universe extends to 46.5 billion light years because we are receiving light that was emitted long ago, when the universe was smaller and those regions were closer to us, and which has been traveling toward us ever since. Those photons have made it across the expanding universe and arrived. But any new light emitted today from those same regions, which are now 46.5 billion light years away, will never reach us. Those regions are beyond the event horizon. We are only able to see them at all because of the ancient light that departed when the universe was young, and those regions were much closer. The event horizon also means that over time, as the universe continues to expand and accelerate, galaxies that are currently within our observable sphere will eventually be carried beyond it, their light fading toward an undetectable whisper before vanishing permanently from our sky. The Virgo cluster, currently 54 million light-years away and still well within our observable sphere, is receding from us right now at a rate determined by Hubble's law. Multiplying its distance by the Hubble constant gives its recession velocity due to expansion alone. This is separate from any peculiar velocity, meaning actual motion through space, rather than motion carried by expansion. For most galaxies at large distances, the recession velocity from expansion dominates completely over peculiar velocities, which are typically at most a few hundred to a few thousand kilometers per second, even for galaxies in massive clusters. The Virgo cluster's recession from expansion is currently manageable, and we will continue receiving its light for an extraordinarily long time. But in the very far future, measured in tens of billions of years, even the Virgo cluster's light will eventually fade as the accelerating expansion carries it toward and beyond the event horizon. The galaxies of the local group, by contrast, are gravitationally bound to each other. Gravity within a gravitationally bound system overcomes the expansion of space locally, holding the system together. The Milky Way, Andromeda, the Triangulum Galaxy, and the dozens of dwarf galaxies orbiting them are not being carried apart by cosmic expansion in any meaningful sense. Their mutual gravity holds them together, and they will continue to interact, eventually merging into a single large remnant galaxy over the next several billion years. Cosmic expansion only dominates on scales where gravitational binding is absent, which means the scale of galaxy clusters and above. Within galaxy clusters, expansion is irrelevant. Between clusters, it dominates. This is why the expansion of the universe is not something you need to account for in everyday life, or in any measurement made at terrestrial or even solar system scales. The distances involved are far too small for the expansion to have any detectable effect. Your body is not slowly spreading apart due to cosmic expansion. The Earth and Moon are not drifting apart for this reason. Even the distance between the Milky Way and Andromeda is, in the long run, governed by gravity rather than expansion. Cosmic expansion only becomes the dominant phenomenon at the scales of galaxy clusters and superclusters and the vast filaments of the cosmic web, where the distances between gravitationally unbound structures are large enough for the expansion to have accumulated into a significant recession velocity. When Hubble first measured the redshifts and distances of nearby galaxies in the 1920s, the recession velocities he derived were relatively modest and the distances modest by cosmological standards. He was working with galaxies within tens of millions of light years, and the data already showed a clear linear relationship between distance and recession velocity. Extrapolating this relationship to much larger distances predicts recession velocities that can exceed the speed of light for objects sufficiently far away. And this is indeed what observations confirm. Galaxies at large redshifts are receding from us at rates that, if you calculate the implied velocity from the distance and Hubble's constant, exceed the speed of light. Some are receding at several times the speed of light. This surprises people because it seems to violate the fundamental speed limit of the universe. But as we have established, the cosmic speed limit applies to motion through space, not to the growth of space itself. The galaxies receding at several times the speed of light are not moving through space at those speeds. They are locally, essentially stationary within their own space. It is the space between us and them that is growing, and there is no limit imposed by physics on how quickly space can expand. The photons those galaxies emitted are still traveling through their local space at 300,000 kilometers per second. Whether those photons will ever reach us depends on the expansion rate at every point along their path. And for the most distant currently observable galaxies, those photons were emitted when the universe was young and the expansion was decelerating, which is why they eventually made it to us despite their sources having been in rapidly expanding space. The redshift of the cosmic microwave background illustrates the extremity of this expansion in the most dramatic way available to observational cosmology. The cosmic microwave background was emitted when the universe was approximately 380,000 years old, at a temperature of roughly 3,000 Kelvin. The light emitted at that time spanned the visible and near-infrared spectrum, the warm orange and red glow of a plasma, cooling toward transparency. Since that emission, the universe has expanded by a factor of approximately 1,100. Every wavelength of that original light had been stretched by a factor of 1,100, shifting it from near-infrared radiation down to microwave wavelengths with a characteristic temperature of 2.725 Kelvin, just barely above absolute zero. The factor of 1100 is not an estimate. It is derived from precise measurements of the microwave background temperature and the known physics of the early universe. This means that the redshift we measure for the cosmic microwave background is approximately 1090. The universe has expanded to 1100 times its size at recombination since that light was emitted. The surface of last scattering, the spherical shell from which this radiation was released, sits at the outer boundary of the observable universe, a distance we will return to shortly. We are inside that sphere. The cosmic microwave background surrounds us like a vast spherical shell, and every direction we look in microwave wavelengths, we see that ancient light from when the universe first became transparent. The detailed structure of the cosmic microwave background carries an extraordinary amount of information about the early universe. It is not perfectly uniform. There are tiny temperature fluctuations at the level of roughly 1 part in 100,000, imprinted on it from the density variations in the early plasma. Regions that were slightly denser at the time of recombination emitted slightly hotter radiation. Regions that were slightly less dense emitted slightly cooler radiation. These fluctuations are the seeds from which all the large-scale structure of the universe, all the galaxies, clusters, filaments, and voids eventually grew through gravitational amplification over billions of years. 2 missions in particular have mapped these fluctuations with extraordinary precision. The WMAP satellite, operating from 2001 to 2010, and the Planck satellite, operating from 2009 to 2013, produced detailed full-sky maps of the cosmic microwave background temperature variations. By analyzing the statistical properties of these fluctuations, specifically the angular power spectrum describing how the fluctuations are distributed across different angular scales on the sky, cosmologists can extract precise values for virtually every important cosmological parameter. The age of the universe, the current expansion rate, the density of ordinary matter, the density of dark matter, the density of dark energy, the geometry of space on large scales. All of these are encoded in the precise pattern of temperature fluctuations across the sky. The Planck mission's results established with high precision that the universe is spatially flat on large scales, meaning that the geometry of space does not curve in the way a sphere's surface curves. Parallel lines remain parallel. The angles of a triangle add up to 180 degrees. This flatness has important implications for the total energy content of the universe, because a flat universe requires a very specific total energy density, and the fact that the universe is flat means that the combination of ordinary matter, dark matter, and dark energy must add up to exactly this critical density. The precise measurements of each component individually, combined with the flatness constraint, give a highly consistent picture that underpins our entire understanding of cosmic expansion history, and therefore of how light travel distances relate to present-day distances. The remarkable thing about all of this is that redshift is not merely a curiosity or a side effect of expansion. It is the primary observational tool through which we map the three-dimensional structure of the universe, measure cosmic distances, and trace the expansion history across billions of years. Every galaxy survey conducted by modern astronomy relies on redshift measurements to determine distances. The Sloan Digital Sky Survey, which mapped the positions of hundreds of millions of galaxies across large portions of the sky, derived its three-dimensional galaxy map from spectroscopic redshift measurements. The statistical patterns in that three-dimensional distribution, particularly the so-called Baryon acoustic oscillation signature, a preferred separation scale of about 500 million light-years imprinted by sound waves in the early universe plasma, serve as yet another standard ruler for measuring cosmic distances and calibrating the expansion history. What emerges from all of these independent lines of evidence, Cepheid variables, Type 1a supernovae, the cosmic microwave background, baryon acoustic oscillations, galaxy clustering statistics, is a remarkably consistent and precisely constrained picture of a universe that began in a hot, dense state approximately 13.8 billion years ago, expanded rapidly in its earliest moments through a phase called inflation, transitioned to a matter-dominated expansion that decelerated under gravity for its first several billion years, and then approximately 7 billion years ago began accelerating again under the influence of dark energy. A transition that is ongoing and that will continue to shape the observable universe for billions of years into the future. Every light year that a photon travels through this expanding universe is not simply a measure of distance. It is an integration over the expansion history of the cosmos at every point along the journey. When we say that the light from a galaxy has traveled for 10 billion years to reach us, and that the galaxy is now approximately 33 billion light years away, rather than 10 billion, those two numbers are related by the entire expansion history of the universe over those 10 billion years. Every change in the expansion rate, every transition from deceleration to acceleration, every influence of matter and dark energy on the growth of space, the difference between the light travel distance and the present day distance is a compressed record of cosmic history. The universe is not a static stage, it is a dynamic entity, continuously evolving, its geometry and scale changing on timescales that are vast by human standards, but are written in the light arriving at our telescopes every night. Each photon that has traveled across billions of light years carries within it, in its wavelength, its direction, and its precise pattern of intensity variations, the imprint of a universe that was smaller, hotter, and different when the photon was born, and which has expanded and evolved through all the billions of years since. Reading that light accurately requires understanding not just how far it has traveled, but through what kind of universe it has been traveling, how that universe was changing during the journey, and what the geometry of expanding space does to the relationship between distance covered and the present-day location of the source. It requires, in other words, everything we have covered here. And it is this understanding that transforms the night sky from a display of points of light into a window onto the full history of the cosmos, a history written in light that has been traveling for billions of years, through a universe that has been continuously growing the distances it must cross, arriving finally at our instruments and our eyes with the story of where it has been encoded in every photon. There is an edge to what can be known, Not an edge in the sense of a wall or a boundary you could approach and look beyond, but an edge in a deeper and stranger sense, a horizon written into the structure of space-time itself, defined not by the limits of our instruments or the weakness of our eyes, but by the fundamental physics of light, time, and an accelerating universe. Beyond a certain distance, no signal can ever reach us. No light, no radio wave, no gravitational wave, no information of any kind can cross from there to here. Not because the distances are merely large, not because we would simply need a more powerful telescope, but because the expansion of space has made those regions permanently, irreversibly unreachable. We live inside a universe that has edges we can identify but never approach, boundaries we can calculate but never cross, a horizon that recedes from every observer at the speed of their own causal influence. And understanding what this means, not just as a cosmological abstraction, but as a physical reality that defines the limits of everything that can ever be known from any vantage point inside this universe, is one of the most profound destinations that the story of light travel across a cosmic time can take us. The cosmic event horizon, which we established earlier, sits at approximately 16 billion light years from us today, is the boundary beyond which any light emitted right now will never reach us. But this is not a static boundary. It is not a fixed sphere sitting in space that the universe is slowly filling up. It is a dynamic limit that depends on the expansion history of the universe, from now into the infinite future. As the universe continues to expand, and as dark energy continues to accelerate that expansion, the event horizon grows over time in terms of its physical distance from us. But its co-moving size, meaning its size relative to the expanding fabric of space itself, actually shrinks. Galaxies that are currently within our event horizon will eventually be carried beyond it as the accelerating expansion sweeps them past the threshold from which their future light can still reach us. This is not an instantaneous process. A galaxy being carried toward the event horizon does not simply vanish from our sky the moment it crosses the threshold. Its light continues to arrive, but increasingly redshifted, increasingly stretched toward longer wavelengths, arriving at lower and lower energies as the expanding space between us and the galaxy stretches every photon that departs from it on its way to us. The last photons from any given galaxy, the ones emitted at the moment the galaxy crosses our event horizon, will be infinitely redshifted by the time they arrive. Their wavelengths will have been stretched to infinite length. They will carry zero energy. They will be, in any practical sense, undetectable. The galaxy will fade from our observable universe, not with a sharp cutoff, but with a gradual asymptotic dimming that ends in permanent invisibility. Think about what this means for the future of astronomy. We inhabit a particular moment in cosmic history, and the observational richness of this moment is not guaranteed to persist. Right now, the observable universe contains approximately 2 trillion galaxies. Those galaxies are distributed across a cosmic web of filaments, clusters, and voids that spans 93 billion light years. The evidence of the Big Bang is written across the sky in the cosmic microwave background. The large-scale structure of the universe is accessible to measurement. The expansion history is traceable through observations of objects at many different distances, and therefore many different epochs of cosmic time. We can, in principle, reconstruct the full history of the universe from the light available to us today. But the accelerating expansion driven by dark energy is continuously eroding this richness. Galaxies beyond the local group are receding, and the rate of recession is increasing over time. In roughly 150 billion years, the Milky Way and the remnant of its merger with Andromeda will be the only structure visible in the sky beyond the immediate gravitationally bound companions. Every other galaxy in the observable universe today will have been carried beyond the event horizon. Their light will have been redshifted to undetectable wavelengths. The cosmic web, the filaments and clusters, and the entire large-scale structure of the universe will have faded from view entirely. The sky will be dark except for the stars of the merged local group remnant, and the cosmic microwave background will have been redshifted far below the microwave regime to wavelengths so long that no conceivable instrument could detect them. Any intelligence existing in that era, looking out at the universe with whatever tools it possesses, would see a very different cosmos from the one we see today. They would see a single large island of stars surrounded by absolute darkness. If they developed cosmology and astronomy, they would observe that island carefully, measure its stars and their motions, perhaps detect the gravitational influence of dark matter within it. But there would be no distant galaxies to study, no cosmic microwave background to analyze, no Type 1a supernovae at large redshift to measure the expansion history with. All the evidence that we use today to conclude that the universe began in a Big Bang, that it has been expanding for nearly 14 billion years, that it contains 2 trillion galaxies in an observable sphere 93 billion light years across, all of that evidence would be gone, erased by the accelerating expansion, hidden beyond a horizon that retreated faster than any signal could follow. Those future observers might conclude that the universe is their galaxy, and nothing more. They might develop physics and mathematics and look for signs of structure beyond their island, and find nothing because there is nothing to find within their accessible, observable sphere. The truth of the universe's origin and large-scale structure would be, for them, genuinely unknowable. Not unknown in the sense of not yet discovered, but knowable in principle. Unknowable in the deepest sense, because the evidence has been physically removed from their causal past. The universe would have hidden its own history from its future inhabitants. We, by contrast, are extraordinarily fortunate in our timing. We exist at a cosmic moment when the evidence is still here. The distant galaxies are still visible. The cosmic microwave background is still detectable. The expansion history is still readable in the light from objects at many different distances and epochs. We arrived at the point of scientific literacy at precisely the right time to see the full structure of the observable universe before the accelerating expansion erases it. 1 billion years earlier, the evidence would have been essentially the same as it is now, slightly cleaner in some ways because more distant galaxies would have been within the event horizon. But 100 billion years later, the evidence would be gone, and no amount of ingenuity or technological sophistication would bring it back. We are, from the perspective of the universe's long timeline, living in a brief window of extraordinary cosmological visibility. This temporal privilege extends to our ability to detect the cosmic microwave background at all. The background is currently observable at microwave wavelengths, with a characteristic temperature of 2.725 Kelvin. It represents the most ancient light in the observable universe, emitted 380,000 years after the Big Bang, and traveling toward us ever since. Its detection in 1965 by Arno Penzias and Robert Wilson, who were trying to identify a persistent noise source in a sensitive microwave antenna at Bell Labs in New Jersey, and discovered to their initial puzzlement that the signal came uniformly from all directions in the sky, was one of the defining moments in the history of cosmology. It confirmed the Big Bang model. It demonstrated that the universe had a hot, dense, opaque past. It provided a direct window onto the physical conditions of the early cosmos. Penzias and Wilson were awarded the Nobel Prize in Physics in 1978 for this discovery. But the significance of what they found goes beyond any single scientific result. The cosmic microwave background is the oldest directly observable thing in the universe. Everything that happened before the era of recombination, the first 380,000 years of cosmic history, is hidden behind it. The universe was opaque during that period, a hot plasma through which photons could not travel freely. The cosmic microwave background is the surface of last scattering, the moment when the universe first became transparent, the earliest moment from which any electromagnetic signal can have reached us. Before that surface, there is no light to receive. This is not because nothing was happening. The Big Bang itself occurred roughly 14 billion years ago. The first fractions of a second after the Big Bang were extraordinarily eventful. The fundamental forces separated from each other in sequence. Quarks condensed into protons and neutrons. Protons and neutrons fused into the first atomic nuclei during a period called Big Bang nucleosynthesis, which lasted from roughly a few seconds to about 20 minutes after the Big Bang and produced the hydrogen, helium, and trace amounts of lithium and beryllium that would become the raw material for the first stars. All of this happened. All of it is real, but none of it can be observed in electromagnetic radiation, because the universe was opaque throughout, trapping photons in the plasma and preventing them from carrying information outward to any distant observer. The only direct signal from before the era of recombination that can reach us today is gravitational waves. Unlike photons, gravitational waves interact extremely weakly with matter and could, in principle, have propagated freely through the hot plasma of the early universe, without being absorbed or scattered. If events in the very early universe produced gravitational waves of sufficient amplitude, those waves should still be propagating through the universe today, forming a gravitational wave background, analogous to the cosmic microwave background, but extending even further back in time, potentially all the way to the inflationary epoch in the first tiny fraction of a second after the Big Bang. Detecting this primordial gravitational wave background is one of the primary science goals of future gravitational wave observatories, including planned space-based detectors and efforts to find the signal's imprint on the polarization pattern of the cosmic microwave background. It has not yet been definitively detected, but the search is active and the theoretical motivation is strong. Inflation itself, the period of extraordinarily rapid exponential expansion that is believed to have occurred in the first tiny fraction of a second after the Big Bang, is responsible for many of the large-scale features of the universe we observe today. Inflation explains why the observable universe appears so uniform in temperature, why the geometry of space is so precisely flat, and why the initial density fluctuations that seeded all subsequent structure have the particular statistical properties they do. But inflation also stretched any region of space it acted on to a size vastly larger than the observable universe, potentially by an enormous factor depending on the precise model of inflation adopted. If inflation occurred, and the evidence from the cosmic microwave background strongly supports it, then the total universe extends far beyond our observable sphere. The exact size of the total universe depends on how long inflation lasted and what its energy scale was. Quantities that current observations can constrain but cannot pin down precisely. Some inflationary models predict a total universe only modestly larger than the observable universe, perhaps a few times larger in each dimension. Others predict that inflation produced a universe so large that the observable sphere, 93 billion light-years across with its 2 trillion galaxies, represents a fraction so tiny that no decimal representation captures its smallness. In the most extreme versions of eternal inflation, the process of inflation never completely stops, but continues in different regions of space at different times, constantly generating new domains of space-time, each potentially as large as our own observable universe, producing what is called a multiverse of effectively infinite extent. These are not purely speculative ideas disconnected from observation. They arise naturally from the mathematics of quantum field theory applied to the conditions of the early universe. They make specific, testable predictions about the statistical properties of the cosmic microwave background, particularly about the precise shape of the power spectrum of temperature fluctuations and the potential presence of gravitational wave signatures. The predictions of simple single-field inflation models are in excellent agreement with Planck satellite measurements. But the question of whether inflation was eternal, of whether there is a multiverse, of whether our observable universe is one among infinitely many, remains outside the reach of current or foreseeable observational tests. Whether it will ever be answerable is itself an open question. What is not speculative is the existence and nature of our observable horizon. The region of space from which we can currently receive signals is precisely defined. The physics governing it is well understood. The equations of general relativity, combined with the known expansion history of the universe, give a precise and consistent answer for the size and structure of what is accessible to observation from our location. And one of the most important features of this horizon is that it is not a special place in the universe. Every observer, regardless of where they are located in the cosmos, has their own observable sphere of the same radius, centered on themselves. An observer in a galaxy a billion light-years away from us has their own observable universe, centered on their galaxy, extending 46.5 billion light-years in every direction from their vantage point. Their observable universe overlaps with ours, but extends in other directions, into regions we cannot see. This is a consequence of what cosmologists call the cosmological principle, the assumption, well supported by observation, that the universe is homogeneous and isotropic on large scales, meaning it looks the same in all directions and is the same everywhere when averaged over sufficiently large regions. There is no center to the universe. There is no edge in the sense of a boundary where the universe stops. Every point in space is equivalent to every other point on the largest scales. The observable universe, centered on Earth, is just the patch of the total universe within our causal reach. It is our observable universe, not the universe, and its centering on our location is a consequence of our vantage point, not of any special cosmic status. The light arriving at our telescopes from the most distant observable objects has traversed almost the full radius of our observable sphere. It has crossed roughly 40 to 46 billion light years of expanding space during a journey that began when the universe was only a small fraction of its current age. During that entire journey, the photon interacted with essentially nothing. The universe is almost incomprehensibly empty. The vast majority of the volume of the observable universe is empty space, with matter concentrated into the thin filaments and nodes of the cosmic web. A photon traveling across the observable universe has a very high probability of completing its journey without ever encountering another particle. It crosses billions of light years of void, threads between galaxy clusters separated by hundreds of millions of light years, traverses the enormous empty volumes of the cosmic voids, and arrives at Earth, having interacted with almost nothing during its entire multi-billion-year journey, carrying within it the pristine imprint of the conditions at its source. This emptiness is itself a profound feature of the universe. We tend to think of space as the backdrop against which interesting things happen, with matter and energy filling it to varying degrees. But matter and energy are, in a very real sense, the exceptions. The vast majority of the observable universe is dark, cold, and empty, containing nothing but the occasional photon and the occasional particle of the diffuse intergalactic medium. The cosmic web, for all its grandeur, occupies only a small fraction of the observable volume. The voids, those vast regions between the filaments where galaxy density falls to nearly zero, make up approximately 80% of the volume of the observable universe. The universe is mostly nothing, with structures of something scattered through it like threads of foam on a vast dark ocean. This emptiness has a consequence for the fate of any civilization attempting to understand the cosmos. As the universe ages and the accelerating expansion carries galaxies beyond the event horizon, the observable universe will not only contain fewer galaxies, but will become, in the observable regions that remain, even emptier. The matter available to any future civilization will be limited to the gravitationally bound remnant of the local group. The intergalactic medium will thin out further as the universe expands. The era of star formation, which has been declining for billions of years already as the reservoir of cold gas available to form new stars depletes, will eventually end entirely. The last stars will form, live their lives, and die, leaving behind stellar remnants, white dwarfs, neutron stars, and black holes in a universe growing steadily colder and darker. The timeline of this long cosmic decline is worth dwelling on for a moment, because it contextualizes the brief and extraordinary period of cosmic history in which we find ourselves. The universe is currently approximately 13.8 billion years old. The era of stellar formation, sometimes called the Stelliferous Era, began with the formation of the first stars a few 100 million years after the Big Bang, and will continue for roughly 100 trillion years into the future, as the longest-lived red dwarf stars burn through their hydrogen fuel with extreme efficiency over timescales many times the current age of the universe. The Sun, a mid-sized star, will exhaust its hydrogen in approximately 5 billion years and swell into a red giant before shedding its outer layers and leaving behind a white dwarf. The smallest red dwarfs will continue burning for trillions of years. After the last stars have died, the universe will enter what is sometimes called the degenerate era, dominated by stellar remnants slowly radiating away their residual heat into an increasingly cold cosmos. This era will last for an almost incomprehensible duration. Black holes, the most extreme remnants of massive stars, and the supermassive black holes at the centers of galaxies persist far longer than any other structure, slowly radiating away their mass over timescales so extreme they dwarf every other duration in this story. These are timescales so vast that the current age of the universe, 13.8 billion years, is not even a roundest error in comparison. The entire history of the universe, from the Big Bang to the present day, is an inconceivably brief opening moment in the full temporal scope of what this universe will eventually contain. We are in cosmic time as well as in cosmic space, located near what might be called the beginning. An early moment in a story whose full length dwarfs the duration that has elapsed so far by factors that have no parallel in any human framework of time. All of this future history, all of these timescales, are the consequence of the same physical laws and cosmological parameters that govern the light traveling toward our telescopes tonight. Dark energy, which is stretching the observable universe apart and which will eventually carry all external galaxies beyond our horizon, is the same component whose energy density was precisely measured from the supernova data and the cosmic microwave background. The Hubble constant, which tells us the current rate of expansion and therefore the current size of the event horizon, is the same constant whose tension between different measurement methods represents one of the active frontiers of observational cosmology. The speed of light, which sets the radius of the observable universe and which every photon in every telescope image has been maintaining without deviation for billions of years, is the same constant that is built into the definition of the meter. Every aspect of this story connects to every other. What does it mean, then, to live inside a universe with a horizon? What does it mean to be an observer embedded within a causal bubble, able to see in every direction to a depth of 46 billion light years, but no farther, surrounded by a cosmos that extends far beyond that boundary in ways that cannot be directly confirmed? It means that knowledge itself has a physical limit, not a limit set by intelligence or technology or resources, but a limit set by the speed of light and the age and geometry of the universe. There are true facts about the universe that are, in principle, inaccessible to any observer located where we are. The regions beyond our horizon are real. They contain matter, stars, galaxies, structures, perhaps life, perhaps intelligence. But none of that can communicate with us, influence us, or be influenced by us. The causal disconnection is total and permanent. This is not a tragedy. It is a structural feature of a universe governed by the laws of physics as we know them. Every observer in every location in the cosmos is in the same situation. Every intelligence, wherever it exists, is embedded in its own causal bubble, able to see outward to the limit of its own observable horizon, and no farther. The universe is not accessible in its totality to any single observer. It is, in a precise sense, divided into causally disconnected regions that can never share information, never interact, never know of each other's existence. And yet, from within our bubble, the accessible universe is staggeringly rich. 2 trillion galaxies, hundreds of billions of trillions of stars, a cosmic microwave background that encodes the physics of the universe's first moments. The large-scale structure of filaments and voids that traces the distribution of dark matter across hundreds of millions of light years. Light that has been traveling for nearly 14 billion years, carrying within it the imprint of its origin, arriving at our instruments with the history of the cosmos compressed into its wavelength and direction and intensity. All of this is knowable, measurable, and to a remarkable degree already known, because the light has been traveling toward us for billions of years, and we have built instruments sensitive enough to catch it and minds capable of reading what it carries. The night sky, properly understood, is not a ceiling, it is a depth. Every direction you look, you are looking outward through space and backward through time simultaneously, seeing light that left its source years or centuries or millions or billions of years ago, traversing an expanding universe that has stretched every photon's wavelength and altered the relationship between the source's original position and its present location. The nearby stars show you a recent past. The distant galaxies show you an ancient one. The cosmic microwave background, barely detectable at microwave wavelengths but mapped with extraordinary precision by dedicated satellites, shows you the universe as it was nearly 14 billion years ago, before any galaxy existed, before any star had formed, when the cosmos was a hot, opaque plasma just cooling enough to become transparent for the first time. Every photon captured by every telescope is a message from the past, carrying information about a source that no longer exists in the form it had when the light was emitted. Stars have aged, galaxies have evolved, some have merged, some have been torn apart, some have formed new stars, some have exhausted their gas and gone quiet. The universe has been changing continuously during the time all this light was traveling, and the light arriving now is an archive of what the universe looked like at the moment of emission, not what it looks like today. We are perpetually, inescapably looking at history. The present state of the universe beyond our immediate neighborhood is hidden from us by the same physics that makes observation possible at all. This is the final and most profound implication of the speed of light applied to cosmic scales. It is not simply that the universe is large and light takes a long time to cross it. It is that the finite speed of light, combined with the age and expansion history of the universe, creates a situation in which every observer is surrounded by a horizon beyond which nothing can be known, and in which everything observable is a record of the past, rather than a window onto the present. The deeper you look into space, the further back in time you see. The most ancient light reveals the universe's infancy. The horizon marks the edge of the knowable, and beyond the horizon, the universe extends in ways that may be infinite, containing more galaxies, more stars, more structure, more history than we can ever observe, regions forever outside our causal reach, separated from us not by mere distance but by the fundamental architecture of space-time in a universe where light has a speed and space has a history. We are inside the universe, looking out from a single point in an expanding cosmos, catching the light that has had time to reach us across nearly 14 billion years of cosmic history, reading in that light the story of where everything came from and where it is going. The light that left a galaxy 13 billion years ago and arrives tonight at a telescope on Earth has crossed almost the full depth of the observable universe. It has traversed a distance of 13 billion light years through expanding space. It has been redshifted by the expansion to wavelengths longer than those it carried when it was emitted. The galaxy that produced it is now roughly 46 billion light years away from us. And the information that photon carries, that single photon after a 13 billion year journey across the universe, is among the most ancient direct evidence of cosmic history available to any observer anywhere in our causal bubble. The universe lit itself up nearly 14 billion years ago and has been sending that light outward ever since. We arrived just in time to catch some of it. The rest is still traveling, still crossing the expanding void, carrying information about regions we will never see to observers that may not yet exist. The light does not know it is being watched. It does not know it is carrying history. It simply travels at 300,000 kilometers per second through whatever space it finds itself in, faithful to the one law it cannot break. The law that says it must always move at exactly this speed, and never faster and never slower, across every distance, and through every era, for as long as the universe endures. That faithfulness is what makes the sky readable. That constancy is what turns distance into time and makes every upward glance an act of archaeology. The universe is vast beyond any honest reckoning, and what we can see of it from here is only the portion whose light has had time to find us. But that portion, those 2 trillion galaxies distributed across 93 billion light years of observable space, is more than enough to reveal the shape and origin and fate of the cosmos we inhabit. The light has been traveling all this time so that we could catch it, read it, and understand, at least in broad outline, the astonishing story it carries.